Okay, welcome everyone. Thank you for coming by. Today is September 19th, 2023, and tonight we are having a special guest speaker, Dr. Mi Lee from the University of Tennessee. He is the assistant professor in biorefinery and polymers and from the chemistry department. You'll hear a little bit more about him later on tonight. I hope that you guys enjoyed our trivia. Looks like there's a few of you guys that really know your stuff. I think the one I got the most kind of conflict was the first one regarding the cells. So I'm glad I got some of you guys on that. Anyways, let's get started. So like I said, today is the 19th of September. So for anyone who is new to Virtual Science Club, Virtual Science Club meets 1 to 2 times a month on Tuesdays at 7 p.m. Excuse me. We have 1 to 2 meetings per month, and the reason why it's only 1 to 2 meetings is because during November and December we do take a break for holidays, and so our meetings are a mixture of mentor breakout sessions and guest speakers. And so next month, next month and next meeting, you will have a breakout session with your mentors that will be on the 10th of October. So the students that are present are from 6th to 12th grade, and there are a few STEM teachers and leaders are also part of this meeting. Again, it's free to attend, and you can register for the next meeting using the QR code in this slide. All right, so we are now open for business for SASEF. The registration opened last September 5th. And so the hard deadlines that we like to outline is the pre-approval deadline, which is on January 18th, the project registration, which is due on February 27th, and then the actual event is going to be on March 26th. And then we're going to take, typically our awards ceremony is 2 days after the event, but we are going to push it back a week just to ensure that we have everything settled and our ducks in a row. So the award ceremony is going to be the following Tuesday on April 2nd. If you would like a more detailed outline of the registration process for SASEF, on the left QR code, we have the SASEF website, and then on the right QR code, we have the SASEF registration info and timeline. The most important thing is if, for all the students, if you are interested in submitting a project, your teacher must first start the registration process, and then you will follow up with them with your information and project information. And so SASEF, the Southern Appalachian Science and Engineering Fair, we have 23 counties that we serve. If you are not part of this county, there are other science fairs available in your area. And if you need help finding out that particular location, reach out to us and we would love to help you out. We're trying to ensure that everyone has access to a science fair that's near them, and of course mentoring through our services. All right. Those are the last of my quick little reminders of SASEF. Now we're going to roll into our Virtual Science Club guest speaker, Dr. Mi Lee. I'm going to provide you with permission, sir, and then you can take over from there.
Okay, thank you, Trixie. So let me see if I'm able to share my screen. Okay, so I hope we can see my screen.
Mm-hmm.
Okay, so let me try to minimize this one. Okay, so good evening, everyone, and thank you, Trixie, for the introduction, and also thank you, everyone, for the invitation. And it's really my privilege to share our work and pretty much the work our group is doing at UTK. And so tonight, the title of my talk is "What else can trees and grasses bring to our life?" And as a correction right here, I'm not from the chemistry department, but I'm working a lot of chemistry work. And I'm actually have been trained as a wood chemist. So you know chemistry chemist, but you probably don't know there is a subgroup is working on the wood chemistry. So I'm associated with the Center for Renewable Carbon and the School of Natural Resources. So with that, okay. So I'm running a chemistry lab at the UT, and I call it a circular biorefinery lab. So with the circular biorefinery lab, I meant by two levels. So basically, we are trying to tap in the renewable materials such as trees and grasses, and to convert it into commodities, materials, chemicals, and fuels. So when I say the circular biorefinery, and you probably heard the word refinery, and refining is basically in the petroleum industry, and you have the the petroleum, and you will refine it and to get a gasoline and a jet fuel and polymers and asphalt and so on and so forth. And the biorefining is basically an analog to the refining in the petroleum industry. So as I said, we are trying to refining the renewable sources like trees, wood, grasses into different types of products. So actually, if you know that UTK is merged by UTIA, Institute of Agriculture, and the previous UTK together right now, these two campuses are merged together. And we are proximate to Oak Ridge National Lab, which is really a privilege. We can leverage the strength of all the three campuses, the agriculture, UTK main campus, and Oak Ridge National Lab. So my lab is a really working a interdisciplinary lab and working on something involved in wood chemistry, chemical engineering, material engineering, polymer science, and food science. And to making the bio-based materials, polymers, and chemicals. So back to the title, the circular biorefinery, and I meant by two levels. And one first level is a material level. So the trees and the grasses are made in nature, and we use it as a material and to functionalize and modify it and make the bio-based products like paper or functionalized paper, absorbents. And so these materials can be used and then applied and then go back to nature. So that's a high level materials circularity. It also means a second level, which is a molecular level. So what I'm interested in is to take the molecules and compounds from the trees and grass and to use that as a building block to polymerize or co-polymerize to making polymers. And this polymer is a special designed because it can be depolymerized back to the original monomer, the building block. So it forms a molecular level circularity. So with that, my group right now, I mentor graduate students and undergrad students as well. And on the top three are three PhD students working with me currently. And for undergrad students, I have already mentored more than probably about 10 to 12. And currently we have three undergrad students. They are from chemical engineering, chemistry department, and a biochemistry department. So our group is, as I said, we are interested in three directions. The first direction, we are trying to use the trees and grass to make a functionalized and smart materials. And second direction is to, as I said, like a molecular level, and it's to synthesize biodegradable and upcyclable polymers and copolymers. When I say upcyclable, I mean it can be chemically depolymerized back to the original monomer, as just explained before. So we are also interested into making value-added chemicals. Okay, so this is the tree in your eyes, but to me, and it's not just like a beautiful view of tree, and it means a lot of commodities, functional materials, adhesives, chemicals, fuels, and polymers and food. And I don't expect you to understand the background, the chemicals behind that, but basically these are all the chemicals or molecules you can make from trees or grass. Okay, so the first question I want to ask everybody is, do you know how tree grows? So right here, this is a small shrub, okay? So the question is, you probably never pay attention to it. And my question is, do you know if the tree, this little bit shrub grow like they are getting expanded, the whole stem get expanded, or is only get adding on outside layer by layer? So give it a guess. If you don't mind, type any. So A is that all the cells in the stem get expanded and separated and then grow at the same time. And option B is only the outside of the tree and getting added on layer by layer. So what do you think? Okay, I see answers coming. Okay, awesome. Okay, I see a lot of B, and the right answer is B. Okay, so let's take a cross view of the stem. Okay, so basically the original stem of the little tree stay over there, and that cell wall dies when they grow year by year. And each year, then that's why you have the year rings of the trunk right here, and you pretty much can see the circle right here. And actually, the only active cell is on the outside of the tree. So right here, shown on the green ring right here, is called core cambium. So only this side is do the cell division and grow, and so that's why it generates the late wood or early wood, and early wood means in the spring and late wood in the fall. So they have different density that generates the yield ring. You can count how old, how many years the tree grow. Okay, so tree, as I said, it's a renewable material, and basically means it can be grow very fast and from the mother nature. So the question is, do you know what is the chemical reaction of the photosynthesis? And we have been told from high school, I guess, and so what is the reaction of there? How can the tree grow? If you don't mind, you can put away whatever you think the answer to the chat over there. So basically, it's like a chemical reaction. Okay. So this is a very simple photosynthesis reaction. So basically, the leaves and take a carbon dioxide from the air, and with the water and with the help of the photon, the light, I mean, and they produce the glucose unit, that's a C6H12O2, and produce oxygen for animals to breathe in. Okay, so, and from my perspective, or people working in the biorefining, and we have to understand what is the ultrastructure of tree. So here is a really good picture to show you the scheme from a very large scale to a very nano scale from top left. And if you look at tree, it's at a meters scale. And then you cut the tree as a trunk, and you have centimeters of the wood, and then you have a wood block, and you have then you take a block and put it in under the microscope, and you can see actually the wood is made of a lot of cell walls and fibers. And if you this is view it from the crosscut, and you can see there are a lot of the holes called lumen. And then if you take only one of the fibers and crosscut right here, and this is the lumen, the empty part, the void right here. And then the cell wall actually is composed of several layers, and typically 3 layers. We call that a secondary cell wall, layer 1, layer 2, and layer 3. And you also have a primary cell wall, and then you have the middle lamina and like the corner of the cell wall between each other. And then you take apart from here and keep zooming. You found that actually the cell wall is made up another fibril, and we call that elementary fibril, microfibril. And then you take the fibril, keep zooming into a very nano scale, and you have an elementary fibril right here, and it's made up of about 36 or 18 cellulose chains, depends on the species. And so when I say cellulose chain, this is a chemical structure for cellulose. And it's when we are using the paper, and that's made of this cellulose right here. So when you look at the cellulose chain, and it's a repeating unit of the glucose, just mentioned from the photosynthesis of the CO2 with the water and generate glucose right here. Okay, so if you look at the elementary fibril, actually you will observe that the fibril is made up of different like shapes right here, actually that describe the crystallinity of the fibril. And right here is a crystalline region, and right here is pretty like amorphous region. So, and this elementary fibril is the basic unit from the materials perspective for cellulose or for the wood, and it's about the width or dimension of about 3 to 5 nanometers. Okay. So when I just mentioned the lumen right here. So actually this is a softwood, like a pine cell wall, and it's a fiber. And simply put, it looks like a straw. And actually, if you cross-cut it, there is a empty void inside of this fiber. That's why you see this empty void right here. It's called a lumen. Okay. So now it comes to what we are doing right here. I'm going to give you 3 examples, maybe 4, but it's basically 2 types, as I mentioned. And first type is the high level circularity. We are using the cellulose, wood, and trees as a materials to making a bio-based functional materials. So right here, the first type of example is some work we have done with the nanocellulose. If you go back to this scheme right here, and the cellulose fibril right here, we call that nanocellulose because of the size of the cellulose and the nanometer scale. Okay, so when we extract the nanocellulose for use, probably most of you don't know how does it look like. This is how it does look like. And this is a nanocellulose, cellulosic nanocrystal, CNC. And this is a cellulose nanofibril. So the difference is, as I mentioned right here, the cellulose elementary fibril, if you only keep the crystalline region, we call that a cellulose nanocrystal. If you have the whole longer fiber right here, we call that a cellulose nanofibril. So this is more like a crystallized nanocellulose. And this is how the CNC look like under microscope. And it's about like, it's hard to see, but this is a 200 nanometer scale. And so it's about 200 to 300 nanometers in length and 20 nanometers, about 20 nanometers in width. And this is a 1% cellulose nanofibril. And it's really like, looks like a gel, both of them look gel, okay? And so the CNF looks under microscope, it's much longer. It's about several or 20 or 2 to 100 micron in length. And the width is wider as well. It's about like 50 to 100 nanometers. So what we can do with these nanocellulose, because they are so small, they can have some special functions or properties. So the first example I want to share with you, we have done is we're trying to make an emulsification of to encapsulate essential oils. So for those, if you are not familiar with emulsion, so basically it's a two incompatible phases, for example, either oil in water or water in oil. And so there, if you blend it and chill it quickly, and it will form a oil in water or oil in water emulsion. So the way you form emulsion, usually you need a surfactant, which is a surface active agent, which means that it's amphibic. It can help you to disperse the oil and to form this oil and water emulsion. Okay, so the idea right here is the traditional surfactants is like a toxic, and it's a small molecules. And here we want to use the nanocellulose as a solid particles to as a surfactant to stabilize the oil emulsion stability. Okay, so the reason we want to do that, because the nanocellulose is very abundant. You can get it from trees and grass, and also it has a very good deformation resistance, and because it can form a really stable droplets. Okay, so I don't want to go too much about this detail because there are a lot of jargons right here, but basically this is how does it look like, the emulsion right here. And this is a hexene droplets in water, and all these are hexene in water. And you can tell from the surface right here, you have some nanocellulose stabilized these droplets. So the research we have done on how this can work is we are using a special chemical called ethyl laurel arginate. This is a chemical structure, and it's a cationic surfactant. Basically, means it has a positive charge, and this is the ammonium head right here. And it also have featured a long hydrocarbon tail, which is hydrophobic. I hope you are not confused by these terms right here. So basically, this is a amphibic compound. So the idea, this chemical is generally recognized as safe in the food industry area. So the idea is when we have the nanocellulose usually bearing a surface, a negative surface charge, and we are going to apply this chemical LAE to interact with the surface to manipulate the positive charge of the head, and then to modify the nanocellulose, then to control the charge of the nanocellulose, then in order to control the packing density on the interface. And the other thing it can bring is this LAE chemical has a hydrocarbon tail, and that can interact with the essential oil because they are compatible to each other. So eventually, we hope this can stabilize the essential oil droplets in the system. And then we will disperse this emulsion into a packaging film. For example, right here is a polyvinyl alcohol film. And then we apply this one for a in vitro and antimicrobial application for food packaging. Okay, the reason it can bring this antimicrobial function is because of the essential oil. Okay, so the beautiful thing right here is all these components, the LAE, the nanocellulose, the essential oil, and the packaging film are all quote unquote non-toxic materials. Okay, so what is the results look like? So this is the film, and we incorporated the emulsion to the PVA film. It's pretty and nice because it's really transparent. Okay, so then we determined the antimicrobial activity, and we first test these film against a Botulism cinerea, which is a common fungi found in grapes or strawberry. And so we have a control right here, which means we don't add any emulsion to the film. And then we have, oh, excuse me, this is only the no film added. And this is the film added, but the film has zero emulsion added. And this is 1, 2, and 4 means we added 1, 2, and 4% emulsion oil, the emulsion into this film. And it turned out, then we measure the colony of the fungi diameters, and it turned out when 1% added, it has a stronger inhibition, and 2% is significantly inhibited the growth of the fungi, and 4% is completely inhibited. And this is a picture of the fungi size, and you can tell the inhibition of this film. And we also measure this one against the 2 other microbes. One is E. coli and the other is S. aureus, because these 2 are very common bacteria, foodborne bacteria contaminated in the food system. And we did pretty much the same thing, and a control, and a 1%, 2%, and 4%. And then we measure the OD is a density of the bacteria. And so for non-added control right here, the bacteria grows pretty well. And in comparison with the control, with the 1% has a pretty obvious drop of the growth. And for 2% is a significant drop, and 4% is completely inhibited. And the same thing for the another strain, the S. aureus bacteria, and it also shows a very good inhibitory function. So finally, and to the right, we apply this package, the film, cover these strawberries, and we then look at them to measure the decay of the fungi. And and different day, and 0, and then until 5 days, and with the different concentration of the emulsion incorporated film. And it turned out with the 1%, 2%, 4%, they all show pretty good improvement of the shelf life of the strawberry. Okay, that's the first story. And the second story is about it's also about the nanocellulose-based functional materials. And Nicholas knows some, because I'm collaborating with Nicholas about this part. Okay, so as I mentioned, the nanocellulose usually bearing the negative charge on the surface. So this is a sulfonated nanocellulose. And what we are doing right here is to leverage the negative charge on the surface, and then to put a metal ion to anchor to first according to based on the electrostatic affinity. And so to anchor this metal ion to this surface, then we will add a chemical, and this chemical will form a coordinate structure, and that looks like a cage. And if you have heard a word, it's called metal organic frameworks. So basically it's made up of metal ions coordinate with organic ligands. And this cage structure is very special because you can tell it has a really void structure in the center, and that void allows this material to have a really high surface area and a pore structure that allows it to can capture, hold, and release chemicals. Then you can apply it as catalyst, absorbents, and CO2 storage, and air purification, and so on and so forth. Okay, so the idea right here, why we, because this is the MOF itself is good, but the problem is for the MOF, it's usually a nanoparticles in powder form. It's hard to process and apply to the real life. So that's why the nanocellulose or cellulose, the role of the nanocellulose come to play. So we can use the nanocellulose, as you know, we can make a lot of type of form, such as the paper, filter, and aerogel, hydrogel. For example, right here, this is a nanocellulose aerogel. So once you have this a form, you load it with the MOF right here. It's a lot easier for you to apply to real life for purification, catalyst, and so on and so forth. From the processability standpoint. Okay, so we made some tests, and again, this is a cellulose nanofibril. It's about 100 micron in length, and then we modify the nanocellulose and to introduce the negative charge on the surface, and then we grow the MOF on this cellulose fiber, and you can tell it's a really beautiful, on the bottom right here, a beautiful picture showing that the MOF are the dots right here, and they are well dispersed along with the nanocellulose fiber. So that means this method works. Okay. So then because MOF, there are many different types of MOFs, and depends on what type of metal ions or the organic ligands you're using. Okay, so in order to test the robustness of the nanocellulose in this idea, and we apply these templates, nanocellulose template, to a few metal organic frameworks, and it turned out this is a ZIF8. It's basically is a zinc and a methyl imidazole linkage. Okay, so this is a HKUST, another type of MOF made of copper, and this is a cobalt-based MOF. And the SE microscopic image below, and it shows you really nice the dispersion of the MOF along with the fibers. Okay, so that means the nanocellulose can work as a really good template for the metal organic framework to hybridize. Okay, so here is a picture to show you we want to verify the metal organic framework is dispersed along with the fiber. So we use a energy dispersive X-ray spectroscopy, and to determine mapping the distribution of the metal ions. So for example, on the top right here is a zinc, and so showing on the red. So basically you can tell the zinc metal ions distribute along with the fiber, and this is for the copper, and this for the cobalt. So the information right here tells you that the metal ions are well dispersed along these fibers. And the table below shows you the surface area. As I said, the metal organic framework is special because it has really high pore structure, which means it has a high surface area. So we determine the surface area, and it turned out that this is the the MOF without nanocellulose, and this is the nanocellulose hybridized one, and for all the three. And turn out that the hybridized nanocellulose and the MOF had a really high, more than 1,000 square meters per gram surface area, specific surface area, which is about a couple hundreds lower than their counterpart. And but it's still really high. Okay, so the next question is how can we use this material? So the first thing we test is can we use that one to absorb like some chemicals like pollutants, dyes right here. So here is a methylene blue, and we dissolve it in the water, and you can tell this dark blue color right here. And then we measure the methylene blue concentration against the different time, and you can we throw the MOF cellulose hybrid to this liquid and let it to absorb, and turn out it has really good absorption capacity. Okay, so here is another picture, and you probably want to argue, well, it's a combination of the nanocellulose and MOF. How can we tell? How can you assure me it's not the function of your nanocellulose? Maybe that one can play the role as well, absorption role as well. So in order to rule out that possibility, we threw just a pure nanocellulose, and this is a methylene blue solution, and this is a pure nanocellulose. You can tell it does show a little bit of absorption, but not that much. And so on the bottom, we put the hybrid nanocellulose with the MOF, and it becomes a very clear the liquid. Okay, so another interesting we did is the combination of nanocellulose of the MOF can show some sensing function. And so what I mean right here is a luminescent function. So basically, if you have the cellulose to the left and under the white light, and then the cellulose MOF hybrid to the right, on the white light, there is no difference between them. But if you irradiate a UV light at 295 nanometers, and you can tell the nanocellulose doesn't illuminate at all, but the cellulose MOF hybrid has luminescence. Okay, so how can we manipulate this function? And so the MOF cellulose hybrid can show a luminescent picture right here. And then we know that this hybrid can absorb chemicals. So then we apply this one to absorb a pesticide called methylpentherine, and so which is a really I think it was banned, but it has been historically widely used in the agriculture system. So the thing we can use it to this one is to detect and sense the existence of this pesticide. For example, if we made a solution of the spiked pesticide from left to right, from low to high, and then we put these cellulose materials into the solution. And then we put a UV light to look at it, and you can tell, and a very low solution, it has a really high luminescence, and gradually, and maybe a little bit something hiccup right here, but in general, it gradually quenched by this absorption of the pesticide. So, and this is a control right here. It's really shining under the UV light. So based on this performance and observation, and we eventually can determine a sensor to tell how much the pesticides left in the aqueous system. Okay, so now I'll switch gear to a second type of my our research is about the molecular level circularity. So as I mentioned, we want to use the bio-derived monomers, chemicals from trees and grass, and then to polymerize and to make polymers like plastics and to make a biodegradable and upcyclable polymers. Okay, so here is a few pictures of our around us, and nobody like that. And it doesn't matter if you are an ocean person or not, but basically the plastic pollution is everywhere. The reason for that is the current commonly used plastic, the polymers are hard to degrade and decompose in the nature. And so each year there are a few numbers right here. And in 2019, the whole world has more than 368 million tons of plastic produced. And as I said, the plastic and polymers are primarily from the petroleum industry and the refinery industry. So more than 90% of these plastic are made from the petroleum industry refining. And you probably know in your neighborhood and you have some recycling of this plastic. However, and on the worldwide level, less than 10% of plastic are recycled, okay? And also, the recycling is majorly contributed by the downcycling. Remember, I used the word upcycling. So the downcycling means you have the bottles of plastic and the staff took it and then sort it and then probably pretty much clean it and crush it into pellets and then re-melt it and re-extrude it and making the polymer or new products. And the problem for that mechanical recycling is that every time you recycle the plastic and you have a downgraded performance. So if you have the bottle and you recycle it, make another bottle, and that bottle is likely not mechanical strong as before or something wrong with it. Okay, so that's called down recycling and the downcycling. And the upcycling, as I mentioned, we want to make a polymer that can be depolymerized back to the original monomer, the building block. And then you can use that building block and to make the polymer again and again to form a infinite cycle. Okay, so if nothing has been changed, and by 2050, and we probably produce 1.12 billion tons of plastic. And at that time, there are probably more than plastic in the ocean than by weight than the animals in the ocean. Okay, so there is another number probably scare you quite a lot. You probably have heard that these are plastic are nasty and disgusting. And there is another one called microplastic. And basically it means very small particles of plastic and about like a micron size. And there was a study about the North America, pretty much Canada and the United States, and found that adults on average each year, adults will consume more than 70,000 microplastic particles, either by inhaling or eating with the plastic containers and something. So you don't know, but we have already consumed more than 70%, 70,000 microplastic each year. Okay, on average. Okay, that sounds pretty scary. Okay, so that was the background of there. So driven us to think about, as I mentioned, why we want to do a second type of research right here is to use try not to use the non-renewable petroleum-based feedstock. And we are trying to shift it to use the trees and grass to use the chemicals from there and take it as a building block, as a monomer building block, and to design the special structure and to polymerize it to make a polymer or copolymer. And this polymer has been synthesized and designed because it can be designed in a special way and to allowing it to be depolymerized back to the original monomer. Then we can take the monomer to repolymerize and depolymerize to form a circular polymers. And this is not a new terminology I created. There are several groups are doing this, and my work right here is trying to use the bio-derived monomers right here, and you apply it, and later on, and by the end of the day, you don't worry about the plastic pollution in the world. Okay. So we made some small progress on this type, and so I hope I can have another chance later on can share more, or you can reach out to me for more details about this type of our research. So with that, that's pretty much I covered. I share with you about 3 stories and basically 3 works we have done recently. One is the nanocellulose stabilized emulsion that can be applied to a food packaging with the antimicrobial functions. And the second story was about the nanocellulose hybridized with a metal organic frameworks. And that can be used as a super absorbent to purify pollution and purify water ecosystem and to sense the pesticides. And the third example is a molecular about circular polymer, and in which we can take the monomer building block from trees and grass and to polymerize, copolymerize, make the polymer, make a plastic, and apply it in the packaging, auto, and in our daily life. Then we can depolymerize it back to the original monomer to form an infinite cycle. So probably before this seminar, you don't know the trees can and grass can bring you much more than just a paper or a firewood in your backyard. So there are a bunch of chemicals and properties you can develop, and some of them have already been developed in the society. So with that, I would like to thank you for this opportunity, and thank you for your attention. And let's see if I have time to answer any questions.
Yes, we can do a
Oh, I
question or
took too long.
we can do one question and then we have to wrap up our meeting. So does anyone have any questions for Dr. Lee? You can unmute or you can type in the chat.
I have a question. May I ask? So you mentioned the creation of the new layers on the tree. And so how long would that process take, each layer being built? Like at what time can you see a visible new layer, I guess?
You mean the growth of the tree?
Yeah, sorry.
Okay, that's just a yearly. That's why we call that a year ring. So each year in the spring, the cell wall division and grow faster. So you have a pretty fat cell wall of there. And in the fall or winter, it grow slower. So that will form a different density in that wood. That's why we can tell, oh, there is a ring of the, actually, it's not a ring, it's just a different density of there. So it's a annual ring.
Awesome, thank you.
Yeah, good question.
Okay, we can conclude. Thank you so much, Dr. Lee, for coming by. We're going to finish up our meeting and present the award for today. So if you can give me a second, I'm going to share my screen. If my computer will allow me to. Okay, so I was scrolling through our attendance, and I was able to find a student that I have not seen on our meetings before. And so, Miss Chen, are you still part of this meeting? Nope, I think she left early. Okay, so Majdi, are you, can you say hello?
Hello.
Hi. Have you ever received our our virtual science club incentive um gifts before?
No, I haven't, but it's okay. Thank you.
Oh, no, if you, well, you're my runner-up. So basically, you can pick from one of the five presents on the left side of that screen, and we will send it over to you.
It's okay. You can pass it to third place.
Oh, okay. I believe Jack, Nick, and Zoe have received a drone before. Zoe, I believe you've had one. Yes?
I have, yes.
Okay. And I think we just sent one for Nick last week. Jack, have you received a present from us before?
Yes, I have.
Okay. All right, so if there's anyone that has not, you can send me an email at prep@utk.edu to select your gift, and then we will send it over to you. If not, then I guess we will save it for the next time. All right, so we are on social media. We have a prep newsletter, which we send out on monthly. So the next one will be in October. We also have our Twitter account, an Instagram account, and a Facebook account. I try to ensure that we have everything updated for SASEF as well as for other programs that are coming up. We do have other programs aside from SASEF where the application is opening. Next month, we should have our governor's school application open, as well as our Tennessee Humanities and Science Symposium. So that will open mid-October, and then the applications will close in January. So if you are a rising junior or senior and have not attended governor's school, and you are interested in going to governor's school, please first contact your counselor, because that starts the process. And then our website does have full details on how to get elected and submitted. So last year, actually earlier this year, we capped at 777 applicants for governor's school, and only 120 of the top students throughout Tennessee were invited. So it is a very competitive program. And then our symposium, top prizes are $3,000 in scholarship money for the regional level, which is us. And then at nationals, you can reach up to $12,000 in scholarships towards your university or college in your four-year degree. So all our programs are especially for you guys who are interested in STEM. So I highly, highly recommend that you apply and see what you can do with what you're interested in. So the next meeting is going to be October 10th. and that's going to be with our mentors. So our 4 mentors will come back, and you guys will be able to go into breakout rooms. And if you are interested in doing a project with SASEF, you will be able to pick their brains and help them, have them help you with your project for SASEF and any other research questions you may have. All right, that concludes our meeting for tonight. Thank you again, Dr. Lee, for coming by for our guest speaker, and everyone else who attended our meeting. I hope to see you next October. Thank you so much. Bye, everyone.